This video is a little review of pH. One of the first things I want to talk about is what I say pH means. pH is power of the hydrogen ion. So if we look at the concentrations, we're going to be able to see a very strong relationship between the pH and the power of 10 that the hydrogen ion concentration is to. So the pH scale does run from 0 to 14, not 1 to 14, 0 to 14, with the lower numbers on the pH scale more acidic and the higher numbers closer to 14 more basic, 7 being neutral and they're in the middle. When we have a pH, we do have some mathematical formulas, and we can press these buttons on our calculator. pH is equal to the negative log of the hydronium ions. Remember, hydronium ion is just a hydrogen ion in water, so it could also be represented here with the negative log of the hydrogen ion concentration or hydronium. Either way works. So if we take this definition that I told you about at the beginning, that pH is equal to the power of the hydrogen ions, if we have a hydronium ion concentration or hydrogen ion concentration of 1 times 10 to the negative 5 molar, because remember those square brackets mean molarity, then the pH, or the power of the H, is going to be 5. If you type it into your calculator, into the formulas that we talked about over here, you are going to end up with the exact same answer as 5. Now, let me clear the board here for a second. If I have that, and I can make that relationship as long as this number right here is 1. It's going to be that exact power. If that is a different number, let's see if I have 2.8. It doesn't really look like a 2, but we'll go with it. 2.8 times 10 to the negative 5. I know that the pH is going to be very close to 5, but it's going to be the pH is actually going to be a little bit lower. And I want you to think about that logically and wrap your head around it. If my hydronium ion concentration is now 2.8 times 10 to the negative 5 instead of 1, it means I have more hydronium ions in there, or more hydrogen ions. So that's going to make it more acidic. So it's going to push it further down on the pH scale, making it lower than 5. So here we can guess it's going to be lower than 5. It's not, but not a whole lot. So maybe 4.6 or something like that. Well, if you plug this into the formula up here and take the negative log of 2.8 times 10 to the negative 5, you're going to end up with a pH that is very close to 4.6. It's 4.55. And that's our pH for this one. Again, we would say that it is acidic since it is lower than 7 on the pH scale. Now, the closer this number right here gets to 10, so again, let's look at another set. So let's say it's 9.8. So if this number is now 9.8 times 10 to the negative 5, again, my pH is the power of the hydrogen ions, so it is going to be very close to 5, but lower. It's actually going to be closer, since this number is close to 10 and becoming times 10 to the negative 4, our pH is going to be close to 4, and it's very close to 4. If you take the negative log of that number, you end up with 4.01 as its pH, and there are no units for pH. Alright, we can do the same sort of thing that we're doing here with pH, or the power of the hydrogen ions, with pOH, or the power of the hydroxide ions. Now generally we really only use this concept of pOH because we can relate it to pH, and they are related by the number 14. So pH plus pOH is always equal to 14. And so if I know one of these, either pH or pOH, if I just take 14 and subtract the one that I know, often it's pOH, we can calculate our pH. pH. Okay, So same sort of concept as the power of the hydroxide ions, but you have to remember and keep in mind what you are calculating. So if it's my hydroxide ion concentration is 1 times 10 to the negative 5 molar, my POH, the power of the hydroxide, is 5. All right. Now, if I want my pH, I just have to take that number away from 14, and I end up with a pH of 9. So this solution is basic. It's on that. It's above 7. All right. Now, what's going on with the sig figs? pH has different sig fig rules. POH is also included in that. So the reason is for safety's sake. If I have a hydronium ion concentration of 1 times 10 to the negative 14 molar, and it went by regular sig fig rules, I have 1 sig fig. So I would have to represent my pH as 10 with 1 sig fig. That is unsafe, and we cannot do that. It is just unsafe. A pH of 14 would be very, very damaging, while a pH of 10 is more like strong hand soap and not harmful necessarily at all. So what we do is we gave pH and POH special sig fig rules. Their sig figs are located after the decimal. So they're located after the decimal in pH and POH. So here, if it's 1 times 10 to the negative 14, my pH, the power of the hydrogen ions, is 14, and I see that there is only 1 sig fig, so it's 0.0. And that's how you do pH. Now, we can also go from pH to our hydronium or hydroxide ion concentration. So given pH, I can calculate the hydronium ion concentration. I have these two formulas, one for hydronium, the other works the same way for hydroxide. It's going to be hydronium ion concentration is equal to 10. Now you're going to find that on your calculator. It's the second function or second function of the log button. So you'll do second log, and you'll have to type in that negative, and don't forget that one because it'll throw off your numbers, pH. Again, for hydroxide, it would be the same thing except to the negative POH to get your hydroxide ion concentration. So if I have a pH of 9.21, and I want to know the hydronium ion concentration, it is going to be, plug this into my calculator, second log, negative 9.21. I need to figure out my sig figs. Remember, with pH, the sig figs are located after the decimal, so this one has 2 sig figs. And my calculator says that the answer should be 1.6 times 10 to the negative 9, and we would expect that number to be 9 since that's what our pH is. And of course, square brackets, the units are molarity. So you can do the same thing with POH and hydroxide ion concentrations, and the worksheet that I have for homework tonight is going to make you practice that, and try and practice with your sig figs and keep those in your mind. I'm going to touch one last topic, and that is acid-base titrations. Now, later on we are going to do titrations mixed with ice boxes, and so I want us to be fresh on both of those. So here we go, titrations. We have our nitric acid and strontium hydroxide. We're going to mix those together in the amounts given, that is milliliters, 24.10 milliliters of a 2.15 molar nitric acid solution is going to be titrated with 15.89 milliliters of strontium hydroxide, and we want to know what the molarity of the strontium hydroxide is going to be. The first thing that you need to do is make sure that you complete a reaction. Please, oh please, do not try and do a titration without completing the reaction. So we're going to use our strategies. You take the first things and write them up here with their charges. Strontium's 2+, and then they're just going to switch partners. Hydrogen's no longer going to be attached to nitrate. It's going to be bonded to hydroxide, and strontium is now going to be bonded to nitrate. And so HOH is H2O, and then we have strontium nitrate, NO3, 2. Then, of course, we're going to need to balance this. It's already driving me crazy, so we'll need to put a 2 here and a 2 here, and that should take care of that. All right. Now, because we're going to be dealing with molarities here, we need to make sure that we remember what molarity is, moles per liter. And in this process, the only way to really communicate between two things in a reaction is through moles. So our first thing when we do a titration is to calculate the number of moles of our known solution. And that's the one where we know both the molarity and the milliliters. And in this case, that is going to be nitric acid. So we're going to find our moles by multiplying molarity times liters. Now, these volumes are given in milliliters, so we have to move the decimal 3 times. There we go. And 1, 2, 3. There we go. And we'll have to erase that and that. There we go. All right. Now we have them in liters. If I take 2.13 molar times 0.02410 liters, I'm going to end up with 0.0513 moles of nitric acid. Oops, I think that was supposed to be a H. We'll try and make it into one. There we go. All right. Now, if I need the molarity of my strontium hydroxide. Molarity is moles per liter. I already have the liters of strontium hydroxide. All I need are the moles. So what I'm going to do is I'm going to take these moles of nitric acid and we're going to use mole ratio to go to moles of strontium hydroxide. So it's going to be moles of nitric acid to moles of strontium hydroxide, and it's a 2-to-1 mole ratio. So that's going to give me 0.0257 moles of strontium hydroxide. And then to get my molarity of it, I just need to divide by my liters, which was given in the problem, or that I collected as I was doing the titration. 9 liters. And so the molarity here is going to be 1.62 molar strontium hydroxide. Okay, hopefully that seemed a whole lot easier than maybe you remember titrations. We will be working with these a whole lot more, like I said. So make sure that you print out the homework and complete that, and we'll be ready to hit the ground running the next time we have school.